So today actually I was planning to cover two demos actually, and one was going to be about the AutoGrad functionality in PyTorch, and the other was going to be a demo of implementation of GAN for a simple MLESA dataset. So before we dive into both of those, if any of you have any doubts, we'll try to cover those first.
Hello, I am Ravi. Am I audible?
Yeah, yeah.
Okay. So, if I may ask, you belong to which field of engineering?
I'm actually doing PhD in ocean engineering.
Ocean engineering. Okay. So, why I was asking is, you may be aware of CFD, right? Computational Fluid
Yeah,
Dynamics.
yeah.
Right. So here I was thinking of, like you see, there are several softwares of CFD like Fluent, CFX, and all. You might have heard of these names,
Yeah, yeah,
right?
yeah.
Right. For example, in CFX, I'll take an impeller for a turbocharger or anything,
Mm-hmm.
and I will run some 20 odd cases with various flow rates
Mm-hmm.
for and generate a performance curve.
Okay.
And here I have run for 20 odd mass flow rates, and I have generated the performance curve. Now I want to augment this result from 20 to 50 or 80, means some unknown values, like I need to cover the range. So is there any way, like even from 20 to 100, if I want to do, or for example, take a duct flow through a channel.
Mm-hmm.
I use some boundary conditions and run it. So next I want to get data for DCs which I haven't used in simulations. For that is what augmenting I mean.
Mm-hmm.
So is there any way we can, using our ML, couple these and do it by any means?
Uh, so I'm not uh, specifically familiar with the problem that setup that you exactly mentioned right now, but in general, like as you may know, like these machine learning approaches, they are not that good at extrapolating stuff. So
Hmm.
let's say some specific scenario that if I didn't particularly exactly understand what you are trying to say, but you mentioned that you did some testing at some different parameters,
Right.
and let's say these values were for which you tested. An
Right.
algorithm might be able to do a well, like an ML algorithm that you maybe train on these observations might be able to do some fitting or some prediction about stuff that happens intermediately, but it will not
Within the
necessarily.
min and max, it can do, not beyond min and max.
Yeah, and it also depends on the let's say the data points that you ended up getting the simulation for. So let's say I didn't collect any data point, let's say close to this range. uh, the phenomena that might really be happening in this region, it may not necessarily be able to capture if it didn't have good data of that region. So multiple of those things actually come into play, but like there are I mean uh, so your point is that you are generating some data using some CFD methods, let's say,
Right.
and then you are looking at some other parameter value which let's say you are controlling some flow rate, and you are considering the output of some different output as a result of this flow. flow rate
Can you
change.
click on the link I shared in the chat if you don't mind?
Okay, I'll try. Okay.
Yes. So if you see that, you scroll down a little bit. The second one, what is a pump curve is what it is saying, and it is head versus volume flow rate.
Okay.
And I generate the curve for given some min and max flow rate. So now
Okay.
I want to extrapolate this for several other, whether it could be design, like here you see impeller diameter, various other things are given over here. So for some other diameter for which I have not run the simulation,
Mm-hmm.
the impeller simulation, I
Okay.
want to get data.
So like you want some data outside of this maximum allowable flow range.
Maximum, that is the second thing. Or if I want to increase it to the left side and increase it to the right side.
Yeah, I mean the extrapolation, as you go further away from the points from which you did collect the data, it might not start representing the reality.
Mm-hmm.
So I mean that is one of the big problems that you would encounter. Like let's say you did collect it. I will try to replicate this plot that you have shown here. Uh,
The x1 left hand side is min and right side is max,
hmm.
and I have run from the values within min max, and here I am asking like if I extend it further on the left side and I extend it further on the right side.
Okay, so you want to actually go in this range?
Yeah, even that is also a way. Yes.
Oh, okay. So let's say in this on the x-axis I have put some volume flow. Okay, and so let's say you
Yeah.
did collect. You are collecting maybe uh, all of these curves. Let's say data of all of these
Right.
curves, but they are at specific values of this input.
Right.
So
Right.
this might be the curve that you are getting for the max impeller diameter,
Right.
uh, and the min impeller diameter. Okay, and some efficiency curve. So the thing is, as you collect data from your, let's say, for now, this is actually your domain knowledge that you know that the curve is actually going to be some looking going to look some similar like this.
Correct.
So this efficiency curve, now you know that there is going to be some point at which it is not behaving like a linear curve.
Hmm.
Then
Right.
that is your domain knowledge that you can actually use in this case, so that you will sample more points towards the higher value of this flow q.
Hmm.
So you'll do run simulations for, let's say, these values, and then
Hmm.
you might not need to run many simulations in this range.
Hmm.
So some of that can be implemented, and then as you can see that these curves are not very high ordered, right? So
Right.
that in that case, if you collect fewer data and you expect the curves to look a certain way, you can actually use that information to do in between predictions.
Yeah, you made some sense over here, where the left hand side it is linear, whereas right hand side best efficiency point it is something non-linear. It could be a parabolic or anything.
Hmm.
So in the parabolic range, I run for five flow rates,
Hmm.
and I want to extrapolate that five flow rates data to some 50 flow rates in that regime,
Hmm.
in
Hmm.
that region.
Hmm.
So can that be done?
So now, let's say what we did just now here. Let's say you did sample uh, 5 points in this region. Uh,
Right.
so what could happen is that the 5 points that you did sample, along with the like, uh, let's say it is able to decently predict the underlying curve, and maybe we will draw in two forms. let's say the real underlying curve was something like that, but maybe a best fit kind of uh, thing from these 5 points might be something like that, for example. So then that actually still helps you narrow down even more region where you can do more tests and get even better understanding of what is that point where peak efficiency can be achieved.
Hmm.
So
Right.
so a fewer sample can actually help you get an estimate of what that curve is supposed to look like. So then uh, if if I know that this point is actually going to give a good estimate, I might you might choose to run a test case at this point also.
Right.
That will help you figure out that it was actually this point,
Yes.
something like that. So uh, ML models, like for such applications, I mean, this is actually happening from a very complex fluid flow, right?
Right.
So,
It's
but
all three-dimensional.
yeah,
Right.
so the the final number that you are getting for this efficiency, that is already, I mean, it's a mapping that has already gone through many nonlinear interactions.
Right.
So there is always a, what can I say, uh, you can't really guarantee that. I hear a lot of. Rao, can you mute your mic? Yeah. Okay. Thanks. Yeah. I mean, what I actually wanted to come to wanted to say that there's already very a lot of nonlinear mapping that has happened between this point to getting this even these 5 data points. So
Right.
we can't really guarantee that ML technique would directly give you the best result on such a case, but it can actually still guide you to understand what more data you need.
Mm-hmm.
So even
Okay.
with few points, you can guess what could be that point.
Right.
Yeah. So that is what I wanted to come to.
So, any of your friends or lab mates, or as you are in the student fraternity and in the lab, that too, ocean engineering means it's fluids and fluids only. Any CFD guy applying? Okay, this was just my thought.
Mm-hmm.
If there are some other thoughts, I would like to get to know, because my understanding on applying AI or ML to fluids is very limited. I should say it at as to be zero. So if some guidance as to where it could be used, if you can check among your fraternity and message me,
Mm-hmm.
that would be helpful. Is that possible?
Yeah, yeah. I mean, uh, for specifically for the kind of problems that you are looking at, I mean,
No,
I guess.
let the problems be different. I just want to know as to where it is being used.
Oh, in fact,
So,
the course instructor Balaji sir, he is also working in this area. So he specifically works
mhm,
in applying machine learning methods to uh, these flow patterns and all of those stuff. So I
mhm.
think you can in fact even contact him. He can actually point you to the correct student who is working on some similar topic in his research.
Something, anything in fluids where AI and ML is applied would
In
be
fact,
of
there
some
is
interest to me.
the thing is uh, what I what we are discussing here right now, that is still not I mean ML really applied to the
Possible.
fluids. It's still a curve fitting,
Hmm.
right?
Right.
So there are in fact a lot of things that are going on currently in research which are working on like you really simulating the entire fluid flow phenomena and trying to
Mhm.
accelerate that CFD method, data collection, all of that through neural networks. So you might be
Mhm.
interested in something called pins, and
Mhm.
there are many more architectures that are coming in like popularity recently. So some of these things I think you might be interested in. My
Okay.
knowledge on these topics is also not enough. I mean, I've just started in my research, but these are some things that I'm currently going to start looking at. So, PINS stands for Physics Informed Neural Networks,
Mhm.
and FNO is another techniques, and in fact, there is a variant of this also called PINO. So, FNO basically stands for Fourier Neural Operators, and
Mhm.
there is a variant of it which is also in like has some similar philosophy to pins, and it is applying the physics informed neural networks to the idea of the neural operators. So I can't give you more details on this because I am also not familiar with
Yeah,
this,
you are just started.
but
Okay.
I
Is
think
it possible? Can you give your email ID so I can mail you
yeah, yeah,
rather
sure.
than I wasting time of everyone in the group? If possible, can you put it in the chat?
Yeah, yeah, just
I'll mail you. Yeah, well, yes,
okay.
I got it. Yes. So you just started your PhD, or it is
Yeah, yeah, I mean, this is first year right now. In fact, this is my second semester.
okay? Good.
So
No, why I asked is because next 1 or 2 years you'll be there, right? If I
yeah,
want to interact with this email ID is
yeah, yeah,
official, right?
yeah,
That's why.
yeah.
Okay, fine. We'll catch up again. Yes, thanks.
So yeah, so I will get back to the. So this is what I was planning to do for today. Uh, I had two uh, demos in mind. One was for the tool called AutoGrad in PyTorch, and another thing for. In fact, this will help understand the code that is being implemented in this for GANs. Uh, so if you guys have any doubts, maybe we'll start with those, or we can directly jump to the code. Okay, I guess no doubts for now. So then we will first look at the AutoGrad. Are you guys familiar with it? So just for a check, anyone here familiar with AutoGrad? Okay. Okay. So the thing is, this is actually probably important with the question that you asked just now. That applying machine learning for this physics stuff. So uh, let's say you are given some. In fact, we'll directly jump to the example. I think that will. Uh, yeah. Is my screen visible? I've shared a code. Yeah. Okay. So the thing is, AutoGrad is, I mean, a very, I would say, a fancy name, but it just all it is actually it's your regular gradient descent or no, not back propagation, the chain rule. it's just a programmatic implementation of that idea. And so this is one of the most commonly used tools for various architectures in most of these physics informed or uh, basically techniques applied to machine learning. So these ML techniques applied to our scientific problems. So most of our scientific applications, they can be written in the form of a differential equation, right? So what such tools like they allow you to do is so various parameters are present in your differential equation, and you want to take the derivatives of the outputs with respect to the parameters that are uh, present in your model. So if you want to do that, this sort of a technique helps. This is actually a tool to get those things. What I will do is here is instead of the documentation example, uh, this is here I have created a very simple function. Uh, so there is a function y is equal to ax square plus sine bx, and here a and b are, let's say, your parameters, and x square, and so as you can see that uh, this might be some underlying physical phenomena. Okay, so this y data that you are interested in, or uh, some output that you are interested in, is a function of x in this form, and since there is a sign, this is already a non-linear function, and but you know from your let's say domain knowledge that it is expected to behave in some fashion like this, or maybe this could be your loss function or your differential equation, but for now we are just considering this kind of an example. So by some reason, for some reason, you believe that this is the underlying function, but you don't know the value of these parameters a and b. So now a typical way we could have done, let's say, for solving such a problem, would be we just use formulate this as a uh, like a polynomial in x, since if we didn't know the uh, like that the function really is of this form. Let's say you didn't know that it is ax square plus sine bx. One way you could handle it is you would consider this entire right hand side as some polynomial in x and try to find the coefficients of that polynomial. But in such a case, then you would always be guessing. I mean, you would never really know whether what your coefficients that you have found, they are really correct or not, depending on the. In fact, I will show you the graph of what this function really looks like. So this blue curve for a is equal to 1 and b is equal to 5. This blue curve is what the real function looks like. So as you can see, it's quite non-linear, and if you are trying to map some polynomial to this such a fit might easily be of a very high order, and you would not necessarily know beforehand that you need to fit a very high order polynomial to such a data. But ideally you can. So let's say you did decide to fit it with a 10th order polynomial, then there will be 10 numbers that you would need to find out basically. But if you had the idea that the function is actually of this form, or this could even be your governing equation, in that case you would directly fit this in, and you would want to estimate these a and b. Okay, but if you want to apply a gradient descent sort of methodology for such a problem, you would want the function to actually. So let's say this is your hypothesis function, ax square plus sine bx, and you want to find what a and b values should be present, so that you get this data from. So the red ones are actually the samples that you collected, let's say, from your measurements, and these are quite noisy. So I've actually added some uniform random noise to it. And so the thing is, from this red dots, you want to figure the underlying blue curve. Okay, but the problem is when you are working on a when you are decided to use polynomial regression, you would have to had to estimate 10 numbers, but having this kind of good hypothesis function can help you find the actual parameters that are better describing this function. So this, let's say you wanted to apply gradient descent sort of ideology to this thing, you would need to find the uh, gradient of this right hand side with respect to A and B, right? So actually I have written the, so this was your hypothesis function, a sine ax square plus sine bx, and so for each of these data points I equal to, maybe, is this part visible? Okay, yeah. So for each of the data points I'm just computing a mean squared loss, and uh, yeah, that's all. But A and B are parameters that I don't know in my training process. Ideally there is a derivative of this entire cost function with respect to A and with respect to B, but I want to keep on descending in the direction in which del J by del A keeps on reducing, right? So uh, let's say I will directly come to the oh yeah, so this is how the function really looks like. So I chose a random set of A values and B values, in fact a grid of A values, A versus B values, the function that we are trying to minimize. So this function here is actually a function of A and B. For me the data points themselves are fixed, so using the data points we have made this function. Okay, and as you can see 1 comma 5, A equal to 1 and B equal to 5, that seems like the minimum of this function. Okay, so yeah, this is what I wanted to come to. So what we do here is actually here. So I randomly initialize my A value and B value to some integer, because that those were my initial guesses for the values, and then we set this thing. So I'm setting a variable ag, okay, which is, you can kind of imagine this as uh, a variable which allows for gradients to be computed with respect to it. Okay, which is what this requires grad equal to true formulation does. Okay, so this is a thing that you can implement in PyTorch. So these are, right now you can imagine them as some, it is similar to what a symbolic variable would be like. Okay, and we have defined some optimizer, but for now just know that ag and bg are some numbers. If you create a function out of using these ag and bg and you try to find the gradient of that function, you can basically get the values of how ag and bg are affecting the gradients of that function. Okay, so maybe we'll come to the core here. So I'm creating a function called compute loss, okay, for each iteration. So I'm trying to do a gradient descent kind of approach here. So I'm computing the loss using all of my data and some current value of A and B. Okay, and you will notice here that we are implementing this thing. So this torch dot sign of B, so that is essential because B that is going to go in our this compute loss function is going to be of this ag comma bg form. This, bg form, which is already a tensor. Okay, and what you do is, so now this loss that you have calculated, this is some function of ag and bg. X and y were actually you can kind of assume them as constants for this particular loss function, as I did here. Okay, so this loss function is actually a function of a and b. Okay, is there any doubt at this point? Tensor is essentially like a extended version of your arrays. You can kind of imagine it that way. So multi-dimensional extension of your arrays and so on. Okay. But this idea that the loss function is actually a function of this ag and bg and not of xy, is that making sense? Okay, good. So this, since it is a function of ag and bg, you can compute the gradient of this loss with respect to ag and bg, right? Is that part making sense? Yeah. So that is essentially what this step actually does. So this loss dot backwards, what it will do is, it will so in PyTorch and all, there is something called a computation graph, and so basically it will keep on storing wherever this ag and bg were used, and in this case we are using it only for this function. So we are computing the loss as a function of this ag and bg. Since I had put this requires grad equal to true argument, PyTorch will keep on what do I say, tracking what is going on with this ag and bg, in which functions it is being used, and whenever I do this thing, loss dot backwards, it is going to update in ag and bg what is the gradient of the loss with respect to ag. Okay, is that part making sense? Okay, hard to digest. Okay, just imagine that when I say loss dot backwards, I am updating in ag and bg a value. Okay, so in fact I will try to run this. Starts here. Okay, so after this point, maybe loss the back. Let's see whether this prints. Okay, okay, it is printing. Okay, yeah. So this part you are seeing here, tensor. So for every iteration, so I'm I'm printing this thing, iteration 0, loss, and parameters, the parameter values basically. I'm simply doing gradient descent. Okay, there is nothing new that is going on actually, but what I actually want you to pay attention to is this thing. So before every iteration, I'm printing this tensor. Okay, and you will notice that the value of this tensor is going on reducing. Just keep noticing this. Okay, is that are you seeing that? Yeah, so what this tensor really is this thing. I'm printing this. Okay, so what we are doing here is I have a function called loss. Okay, which is a function of this ag and bg, and whenever I try to compute a gradient, or I'm trying to go back on the loss curve, I mean, or rather go in the direction of decreasing value of this loss curve, there are only two parameters for in this function for which this requires grad this argument is true, and one of them is ag, other is bg. Okay, and when I'm trying to do this step, what PyTorch will do at the back end is that it will update the gradient of this ag value. So it will basically update that it will basically keep track here that this ag variable, it has been used in calculating this function loss. Okay, ag bg are holding gradients for last iteration. It will keep on holding the gradient of this loss with respect to itself for all iterations. I mean, for every time you update the every time you calculate the gradient of this loss function, it will update it. Okay, so this ag dot grad is essentially d loss by d ag. Yeah, update to the latest value of the gradient, that's all. So because ag itself is changing, right? As you do gradient descent, you are going closer and closer to the correct true value of ag, a and b. So the value of the loss function, so you are evaluating the loss function, this is the loss function, you are evaluating it at points closer and closer, you keep on going closer and closer to the true values, the minima. How are we tracking if it's not a local gradient? No, you are computing only the gradient. It doesn't tell anything about whether we are going to a global minima or a local minima. None of that. It's only computing. Let's say I'm right now present at this point -1, 5, let's say, which will be somewhere here. It will just calculate the gradient of the loss function with respect to ag and bg. That's all. Which is going to be a vector. So the del, when will it stop iterating? It will stop iterating when my iterations run out, or when I check this thing. So I'm checking whether the previous loss and the current loss, there is a difference of there is not much difference between them. I will stop the process. Okay, so here I had put a very big number for number of iterations to do, but as you can see here, it goes to about, so it went to about 295 iterations only. The change in loss is much smaller than the threshold, so it has stopped. Okay, so this is actually the point that I wanted to get you. So in fact you can even look at the values of a and b that it ended up converging to. So based on the data points that we gave it, those noisy data, it ended up figuring out that A is 1 and B is 5. So what you achieved something in only two unknowns. What if you had implemented polynomial regression, you might need to, let's say, use 10 values. Okay, so that is the power of rather we can say of using a good hypothesis function. Yeah, I mean, you would not always know it what that function is. This was actually just a dummy example. The thing is, uh, this function that we just talked about, it in case of, let's say, physics informed, you are implementing something which has to adhere to some physical law, let's say some conservation principle, let's say conservation of mass, conservation of energy, something like that. In that case, you can force the uh, entire thing to follow. You will basically compute the loss as some current energy minus and the next energy, basically. Yeah, it is, in fact, whatever I'm just describing here is actually uh, very important to the idea of applying neural networks to machine learning. I mean, neural networks to all these physics based ideas. So if you want to apply neural networks to physics, let's say CFD problems, this actually is somewhere closer to its roots. As we just before the start of this session, we actually discussed. Okay. Yeah, I mean, you can go back and check it later. So that is what I wanted to share about AutoGrad as a method. So this will be heavily used in a lot of ML applications, and so I will now go to the other demo. Uh, Before we go to the GANs demo, is there any theory that I need to cover?
Vallabh,
Yeah.
a run through on GANs, a
Hmm.
walkover, a short brief.
Okay, so some of the theory.
Yeah.
Okay, sure. Okay, actually, there is only very little thing that we actually need to discuss. So I hope the you have gone through the lectures, right? The week's videos.
Yes,
Yeah.
yes.
So I'll just in fact just go briefly over the loss functions that we are actually dealing with in case of GANs. Okay. And then while we are implementing it, I will go through the setups in basically the order in which we keep uh, implementing it. Okay.
Sure.
Okay. So basically, what a GAN network, as you know, is there are two components to it. There is a generator and a discriminator. And the thing that we need to know here is that the generator is actually supposed to return something. So for the generator, input is going to be our some noise, and it needs to learn the mapping from this noise to some output that you are interested in. So in our specific example for today is actually going to be uh, some images of digits. So the network really needs to learn from some random noise that I'm going to put here. It needs to learn what how to create, or how to create something that looks like a number. So it could be like some 1 or 2. It has to create it has to basically light up only those pixels which make it look like a number. So that mapping, that from noise to a desired output, that is what your generator needs to learn. Okay, so I will just put here a image, desired image. Okay, whereas this discriminator is actually a network which can take in an image and it can output a binary uh, result on it, whether that image is fake or a real. So real in our case is the image actually obtained from your training data itself. So this MNIST data set, it has lots of images of humans who have really written these digits out, and we have taken photos of those. Those are your real data. So that is how you expect the digits to look like. So this discriminator, it needs to if a real image is fed in, it needs to find out whether it is real, and if a fake or some noise kind of thing, or something that is not a image of a digit, in fact it could be anything, so if anything you pass in other than a real digit image, it needs to tell that this is a fake. Okay, so these generator and discriminator, they have this kind of competing objectives. If you set it up in this form, I will mainly highlight this part. Okay, so we are making forcefully compete the generator and the discriminator. Here what we are, this is very similar to your binary cross entropy loss. Okay, just that the terms here are slightly different. This part here is your so x is some data that is obtained from your data distribution. So whatever is from your real data set, if you sample something from that, so that is what this thing denotes. If you sample some x from your real data distribution and feed it to your D for discriminator, so whatever will be the output of that, so if you feed in a real input, the discriminator should classify it as 1, right? You should not classify it as 0. So closer to 1, the log value is going to be closer to 0, and closer to 0, the log value is going to be minus infinity. The log curve looks something like that. Right? So we want our this part to be closer to 0. Okay, so whenever I feed in the real data to this discriminator, it should classify it as 1, and the log of that will end up being 0, and you want to maximize that. Okay, the other thing is, it should misclassify, in fact it should properly identify that instead of this x, if I have this z as my input, So z, and here this actually pz of this is actually denoting a noise. Okay, so uh, some noise from sampled from some distribution. Okay, so z is some noise vector, and it is also sampled from some distribution. It could be a Gaussian, whichever distribution you train it on. So it there is some underlying distribution to the noise as well, and you basically feed that in to your generator. And as we know that we want the generator to map from that noise to the what can I say, the actual image that it needs to generate. So this part will happen from your current whatever is your current training level of your generator. It will take in this uh, noise vector, map it to something in the image space, then you apply discriminator on that. Okay, and you basically do 1 minus of that. So if the discriminator, ideally discriminator should be able to identify if the image is fake. Okay, so in the start of your training process, the discriminator is generator is going to be bad. It's not going to be able to generate very good numbers. Like it will be more closer to the noise that it was fed in. So it doesn't do any mapping on it. So it will in goes noise, it will generate out noise only. So in that case, the discriminator should be telling that this is a fake. So it should return out 0, and you again do 1 minus 0 and log of that. If you return, then that will again be closer to 1, and this value is also to be maximized. So basically, since it is sum, you are maximizing both parts. Okay, is this part making sense? Whatever I described with respect to discriminator. Okay, then we have the generator part. So actually generator is also, since it has a exactly opposite objective as the discriminator, and in fact it is trying to minimize this entire thing. Okay, this for entire thing. But what we are, since this entire part is not a function of the first term is not at all a function of the g, right? So there is no gradient of this term with respect to g or the parameters of the generator network. So we are only interested in the second term for the generator part. Yeah, and that is what is this part. So we can either frame it as minimize this thing, so basically the generator has to keep on generating images which are closer to the reality, so that the discriminator is not able to correctly classify them as fake and real. So if the generator gives outputs an image which is very close to what a real number image would look like, the discriminator will not classify it as 0, instead it will classify it as 1. So if that ends up happening, this will be 1, and 1 minus 1 0, and log of that, so it will be minus infinity, right? So the goal of the generator is actually to go towards the minus infinity, and basically to minimize this thing. And you can similarly write that same thing as maximizing the, so here 1 minus is there, you will notice it's 1 minus d of something, but I remove that 1 here, and I can also frame it as this thing. So maximize this quantity by changing the parameters of g. Okay, is that part making sense? Okay. Yeah, in fact, yeah, that is all that from the loss function point of view we can look at. So now I think we will go to the code and parallel it with whatever the loss functions that we saw here. Okay, so you just need to know that this is very similar to your binary cross entropy. Okay, so that is precisely what I'm going to use in the, because the data that I'm going to use from MNIST, it's actually only in terms of zeros and I mean the pixel values. So it's a single what can I say? Yeah, it's within the range 0 to 1 and it's only one channel. There are no multiple channels. It's black and white digit images. Okay. So now we will go to the code. Okay, you already saw the. Okay. So is my code visible? Okay. Before we go to the results, I think I will first go through the description of the code. So what we are doing here is that we are defining the two networks, the discriminator and the generator network. Okay. And since this is a very simple data set, we are using a simple feed forward neural network. Ideally, if you are training for much complex data, you might let's say big size images, you might need to incorporate convolutions, and that would be more ideal. But for this simple data set, we are going with a simple feed forward neural network. Okay. So as we saw, the discriminator's job is actually to take a real input image and return out a single 0 or 1 number. That is what the final layer sigmoid is going to. So it is going to return out a probability from 0 to 1, and whether the closer to 1, it's basically a true image, closer to 0, it's a fake image. Okay, and that is what we are doing here. So the forward, so whatever will be my input image, I'm first making it into a single vector, single dimensional vector, by stacking all making it into a column, and then I'm applying the fully connected neural network that we have defined here, and that is what the discriminator is going to return out. Okay, so in goes the image, out comes the probability between 0 and 1 of it being real. Then we have the generator network, and the job of this thing is to basically take the noise, which is this input dimensional size, and convert that into a image, which is the output dimension size. Okay, so that is the mapping the generator needs to learn, and here that also we have put it as a feed forward neural network. Okay, and yeah, it's the same thing. So x here is my input dimension of the noise vector that I'm using, and from that I'm generating a image. Okay, so far any doubts? Doubts? Oh, clear. Okay, fine. So what we have looked at till now is what is a discriminator, which is a simple neural network, feed forward neural network, and the generator, which is also a feed forward neural network.
One quick question,
Yeah,
Vallabh.
yeah,
The tan h what you used in generator, you
mm-hmm.
said sigmoid over there is 0 and 1. What
Yeah.
does tan h do here?
Tanish will return something output in -1 to 1.
-1 to +1.
Yeah.
Okay, right.
Okay.
Yeah, got it.
So the output of the generator is supposed to be that image, right? So that can be, since we are actually normalizing it here, so that is allowed to be uh, uh, yeah, I mean even in the, I think the output will still end up being in the range 0 to 1 only, but that this is like so for every pixel we actually need to apply that, so we have just randomly chosen it to be 10H.
Okay, yeah, thanks.
uh, then this is a common practice, so we first need to actually convert the entire data set to a tensor. So this MNIST data set, uh, that will be in the form of arrays, but as we saw in the previous section on AutoGrad, you want to convert it to uh, the tensor forms. So everything that you use in PyTorch has to be a tensor. Okay, your data has to be in tensors, your models have to be in tensor, everything has to be in tensor. So that is what this thing will do. And so why are we doing, in fact where are we using this thing is here. So the entire data set you are first transforming it to a tensor, and then you are using this train dataset object in this data loader. So this data loader is something which is very commonly used in machine learning and deep learning applications actually. So what this is going to do is it's going to uh, put your entire data set into batches, okay, and at a time it will only load this batch to your RAM. It will basically not let the not dump the entire data set into your RAM and basically cause problems for your system. It will try to uh, load a limited amount of data at a time, and all your gradients are then computed using this limited data only. So that is the catch here. So the loss function that I previously showed, so at a time you will be having access to a fewer data points in the uh, total data, and you will be computing loss with respect to those. Okay, is that part making sense? So when I talked about the loss function in the previous example, the AutoGrad function, there x and y, I am not passing the entire x and y data set at a time to compute that loss function. In uh, in these applications we are typically passing fewer of those, so only 64 of the x and y, but a and b will be, I mean the parameters of your function, that is still, the function is still a the loss function is still a function of your uh, parameters of the networks that you are training, but the constant parts they are actually limited. Is that part making sense? Hello? Is that last part making sense? Yeah, okay. So basically I was trying to tell the batch size, what the implication of a batch size is. Then what we do here is we are checking if our device has GPU access. If it does, let's use it. And so this z dimension is actually the dimension of the noise vector which I am sampling. Okay, so which is the input to my generator. Okay. There is some, so please let me allow other mobile. I mean you can log out and log in, no problem. The session is getting recorded, so you can cover up the part, no problem. Okay, so this is where we are. So our noise vector that we are sampling is actually of 100 dimensions, and the normal MNIST data says it's actually 28 cross 28. Okay, the images in the MNIST data set, they are 28 cross 28, which is some 700 something. But the mapping that we are achieving with our generator is from this 100 to that 28 cross 28. Okay, so MNIST data set, we are just taking the size 1 and size 2. Okay, so which is going to be 28 cross 28, and here we are defining the generator, which takes in the input the z dimensions, which are the 100 numbers of the noise, and it will output the MNIST dimension, which is 28 cross 28. And you will notice that we are sending the generator model to the device. So since we have GPU, you have to load the entire model onto GPU. Then the discriminator part, the same thing. Discriminator needs to give out 0 or 1. I mean the probability of the image being real or fake, and to it the input is actually the image that is actually generated by your generator. So the output of generator is this 28 cross 28 image, and that is going as the input for your discriminator, and we are loading that also to our GPU. The loss function that throughout, as I said, we are going to use this binary cross entropy loss, and the learning rate is set up here, and the optimizers for both generator and discriminator, we are using the Adam optimizer with the same learning rate here. And you can explore different learning rate, how that works out. Maybe I didn't share the Colab notebook yet. Okay, so if you, when you want to check through the code, you can go through it. Okay, so now we come to the training loop. So we are training it for 100 epochs. What we are going to do here is from our data set, the train loader. So this train loader is this thing that we defined above, this thing, which is picking out from the total data set 64 images of digits at a time, and those are being fed for training. So this batch size is going to be 64. So these are our real images, which are the images of our data set, and we need to load them also to the GPU at a time. So you are not loading the entire data set to the GPU at once. You are loading batch wise. Okay, and this is just for this iteration you need to set the variables for gradient to 0, and you will compute those here in this process here. So yeah, as I described when we are talking about the loss, so what we are doing is we are computing the discriminator's output for all these real images, and the discriminator's job is actually to give output 1 for all of the real images, right? So we are training the discriminator to so the output of discriminator is this real output variable, and we are checking it with this real labels, and as you will see here that all of them are ones. Okay, so I'm taking 64 inputs, all of value 1, and that is what I'm comparing the discriminator's output for these real images to be. Okay, so the discriminator needs to get, if it's working correctly, it should get out 1 for all the real images, and that is how we are computing the loss. Now this loss, since I fed in this real output, and this real output is a function of discriminator, I mean the output of discriminator, so whatever are the variables that are present in the parameters that are present in this discriminator function, that is what the real loss is also a function of. Okay, so is that part making sense? The real loss is function of discriminator's parameters. Is that part making sense? Okay, the real loss is a function of discriminator's parameters, and when I will take the gradient or this real loss dot backward, I'm going to update the gradients of parameters in the discriminator network, as we saw in that autograd example. The AG and BG, similar to that. So with this thing, I'm going to update the discriminators parameters, the values. So discriminators parameters, let's say there is some parameter A, I'm updating the gradient of that parameter with this. And same thing we do with the fake images. So whatever is our generator right now, the level up to it is just trained, will feed in some noise. So the noise now needs to be batch size cross z dimension, so which was 100. Okay, so that is the thing that we fed in, and the generator generated. So from this 64 vectors of each of 100 dimension of noise, the generator is going to generate 64 fake images of digits. And when the discriminator's job is now to output 0 for all of these, because they are generated by the generator, they are not part of the real data set. Okay, so that is what we are calling the fake labels. Okay, and then the loss that we are going to look at is between these fake labels and the outputs, which are going to be, so here you will see I'm setting it as zeros. So there are 64 zeros, and that is what the discriminator should be doing. So all of this that we are doing here is actually to get the update the discriminator. Okay, all of this is for training the discriminator. Is that part making sense? Because everything is a function of discriminator, and also a generator here, the fake images themselves, but it goes through the discriminator to update. The PyTorch will keep track of what all parameters were involved in getting us to this stage. Is that part making sense? Did I lose anyone here? Okay. So then we step in the direction of the reducing gradients. So here we are optimizing our discriminator. Discriminator is handling AG, BG here. Discriminator is not handling AG, BG specifically. It is handling some parameters. The AG, BG were just some parameters of our network, right? Of the function that we were looking at. So discriminator is actually here a normal feed forward neural network. So it has some like in last example, it has some of its own parameters, and those are getting to get updated. Okay. Yeah, hidden from user. I mean, uh, it's part of the network. They are not necessarily hidden. uh, you can extract them out when you are doing inference. You can try test check them. Okay, but we are moving in the direction of the loss. I mean, we are going in the reducing the loss for this uh, discriminator by stepping in the direction of steepest descent for the gradients. Okay, then we are going for the, so now all of this is going to be for updating our generators parameters. So what generator needs to do is it needs to get the discriminator to make a wrong judgment on whatever it generated, right? So the discriminator, when it is passed in the fake images, it generates this fake outputs. So this is a 64 dimensional uh, vector which is in zeros and ones. Okay, so we want all of them to be actually 1. I mean, if the generator has done its job very well, all of these fake images are going to look more or less like the real images, and the discriminator is going to return them all of them out as 1. Okay, so we want our the loss for the generator is actually between this fake output and all ones. So the real labels is all ones, as we saw here. This. Okay. And then we do the gradient descent for our generators parameters, step them, and we keep on repeating this procedure. And here we are just going to see at each iteration what is the generator's output looking like. So maybe I will we need the cursor. Okay, so yeah, so you will notice here that in the very start of the training process, uh, the generator was fed in some noise, and the output that you are actually seeing here is what the generator is capable of doing right now at a particular iteration. So in the first epoch, the generator is fed in some noise. All the pixels are some random values. Rather, it's not actually all these pixels. It's a 100-dimensional random vector noise, and whatever mapping that the generator currently has from that 100-dimensional input space to the 28 cross 28 space for the image, it is going to get it is going to do that mapping. So in the first epoch, you will notice that it is really bad, and this doesn't look like any digit or anything. In fact, it doesn't have any lines or any of that thing. But as you will see that since most of these the data, the number is actually somewhere in the middle, and there is a lot of black space around it. So at least the generator is now learning that aspect as we move down the iterations, and then it is slowly learning some more patterns in the thing. So it is trying to make out some, yeah, here the outputs are starting to kind of look more like some edges are being introduced. Okay, and that same procedure we keep on implementing, and over the, let's say, about around 68 epoch, the output is looking like this, which is very close to what we would think 1. but not necessarily not all outputs are that good, but it's trying, making more sense, right? So compared to the noise that we were seeing before, it's now resulting out in some edges and stuff, and you might consider it at some number. Okay, and over this around 100 epoch, this is how the output is like. And after the entire training process is done, I will just, yeah, so these are the results of what the generator is capable of doing after the 100th epoch. So we can keep on checking. So every time it is generating 5 images out of from some 100 dimensional input noise. Okay, so the mapping is not foolproof, but it has still learnt that from a 100 dimensional random numbers what a real number should look like, basically. Okay, so yeah, any doubts at this point? After training, what is the next step here? So whatever I showed here is, I mean, there is no specific, this is actually just a toy example, but what GANs could be used for are, there are many actually variety of applications that GANs can be used for. So one of them is actually, in fact the most popular one is actually generating more data. So as you must have seen in the lecture note, the week's lectures, so if you don't have uh, a lot of real data, you can train a network to basically generate more data which is similar to the real thing. And what you would do is, let's say you want to train some classification model or regression model, you would use that extra, so whatever is the real data plus some distribution that you learnt from the real data, you will create more amount of fake data and add it to your real data and train more models for classification or segmentation and stuff like that on this combined data set. Okay, and another one of interesting applications that can be done is, so uh, maybe I will switch to the tablet. So one interesting thing that can be done uh, with GANs is actually on these lines. So let's say you had some image and it has some characteristics. So let's say in case of basically underwater images, let's say you are interested in transmitting there is some bot, some robot that is operating underwater, and it is observing some data. So there is some vegetation, something underwater, and you, or some fish, some object, and you want to transmit the information that this bot is seeing to some surface station. Okay, so some human operator is sitting over here on a ship. Okay, so typically this one way of doing this is just connect a tether from the ship to down to the bot and transmit that entire data. But in such a case, uh, it's I mean there is a limitation on how much the bot will be able to explore around, right? So in such a scenario, you might be interested in letting there not be a tether here. You want the communication to be wireless, okay? But if it is wireless, then the problem that comes is the bandwidth. Okay, so you might uh, to transmit an image which is a much high dimensional, I mean it's a rich data, right? So there are many numbers that you need to send to really replicate an image. Okay, so in even in this let's say your image size was some 224 cross 224, and it's a, let's say it's an RGB image, because you might be interested in what are the colors underwater also. Then in such a case, this might easily be translate end up becoming some order of 1,50,000. Okay, and you don't want to send all of these numbers, keep on sending them to get a live video feed of what is going on below. Okay, because that is going to be very expensive on the bandwidth. Your bot basically the underwater communication module that you are using, that's not going to be able to transmit so much of data easily. Okay, so in such a scenario, you might be interested in doing something like an image compression. So what you will do is you will feed in a lot of images to a network. Okay, you will basically train a network to compress what a general underwater image might look like, and try to get a latent space, a much lower dimensional representation of whatever is present in this image. So this image is actually, let's say, 224 cross 224 cross 3, and you might be able to compress it to just 500 numbers. So now with this, just compare the ratio of these two, you actually achieved a 300 times compression. So typically whatever is underwater, you can then compress it to just 500 numbers, and then you send these 500 numbers. So the encoder part, that you might call this, that can sit on your bot in the control, in the processors on the bot, and it will compress this image that it is seeing to this 500 sized vector, and it will transmit this 500 instead of this 1,50,000. And the at your surface on the ship, there is another computer which is basically converted these 500 numbers and expanding that to the same output as your decoder, which is again the same output as your input image, which is again 224 cross 224 cross 3. Okay, so basically you are training a encoder and a decoder type network. Okay, is that part making sense? Good for Mars mission. Yeah, possible. Yeah. In fact, they might be having much better ways of doing this than what we are discussing here. That okay. The problem with using it for something like a Mars mission could also be that you need some real images of what a Mars image should look like, right? So whatever your bot is seeing, you need to have good enough data set of that. No, I mean, that wouldn't be really correct, right? uh, Whatever is exactly on Mars is not something that you will see on Earth. You need to get, so if you want a really good uh, image of what is present on Mars and you want to transmit that, you will need to get the data set also needs to be that rich. Then only then the decoder will do its job well, right? Else it would not be able to do its job that well. For a new input image. So what I actually wanted to come to from this thing is that, so let's say you trained a network, a generative adversarial network in fact, so that you feed in a image which is, let's say, of lower quality. Okay, and what you do essentially is that you try to get a higher quality or super resolution image. So basically what you are doing here is that to this real image you are adding in more details which are not really part of the, or these are not present in the real image. So what those details, so you are basically putting a GAN network here. Okay, so what this GAN network is really trying to do is it is trying to generate more details into your picture. So what you will do is you will first get a, you generate a huge data set of lower resolution, poor resolution image, I would say, and super resolution images. And what you are going to do is you are going to feed this in to your GAN network. It will try to add some more details to the picture, and it will make a, it will just create something basically for initial few iterations. But you want this GAN network to learn uh, to add more details into this poor resolution image. Okay, and eventually, so you will basically see you will also have a discriminator which is now checking whether the details added by your GAN, the generator, and the data set of the real super resolution images, so that they all go to the discriminator. And the discriminator is now learning whether, trying to basically figure out whether the super resolution image that you fed in, whether it is from this the real data set or whether it is the fake addition of by the GAN, the generator part. Instead of writing GAN, I will just write generator. Okay, so you could also have a philosophy like this and basically keep on training this generator discriminator so that you end up learning a generator which can take a poor resolution image and make it into a super resolution image. Okay, and then you can use this, whatever you achieved with this generator, you can put it after what you get from your decoder. So in general, whenever you are transmitting information, so the details are actually what are adding up the more information, right? So you could compress it and get some I mean, you will compress it as much as you can, but you are going to lose some information. The part that you are losing after doing this compression decompression thing, that part is actually some of the details, and you can use then a GAN network to actually learn those details in general and then generate an output which is a good resolution image. So is that part making sense? So that is how a GAN would supplement compression algorithm. Any doubts at this point? So this is actually one cool application that can be thought of GANs. So yeah, I mean that is all I. Okay, there is a doubt. What about those AI sites where we can generate images based on text? Uh, okay, do you mean something like DALI or Sora? That is actually a much more complex problem. I mean, I even I don't know much about the details of the networks that are implemented there. But were you present for that lecture when I covered the uh, basically the image captioning problem? So the idea of this was that you basically have some image and there is some caption associated with it. Okay, so some human has labeled what is there in that image, and what you do is that you try to get the network to understand. So let's say we'll take some example. Let's say there is a person in this image. Okay, and this person is, let's say, playing football. Okay, so uh, from this image someone must have so a human must have labeled this, put a caption for this image that a person, maybe some specification about the jersey of that person. So a person in red shirt and so on is playing with a football of white color on a green ground, something like that. So all of these details are present in this caption. So maybe I'll write it down. Person in red. Okay, so what so this image captioning example, basically what I tried to show in that was actually that uh, the network can actually understand using these LSTMs, and uh, so this entire sequence, oops, so this entire thing, the caption, can be interpreted as a sequence. Okay, so this sequence will have some these words are there, right? So, which in common ML or thing literature, they the lingo is something called tokens. Okay, so there are some important words here, like let's say person, red, let's say shirt, maybe, or maybe the football. Okay, so all of these are some objects in this image. If you train this model, the image captioning model, with many images, okay, so many images along with their captions, eventually the network will kind of get an understanding of what in this image actually is a person. Okay, so it will basically learn that over the course of many iterations and your training. It will learn to get the uh, relation. It will understand the relation between the token for person and what in the image corresponds to that. So this I covered. I didn't cover the entire code in much detail, but it will be in some of previous weeks. uh, okay, you can maybe go through that part, but eventually you do learn, let's say, some mapping or some what can I say, the relation of this world person with what is in the image. So that is what the goal of image captioning would be. So once you have learned that out, you can train a model to start uh, generating what a person would be. So you will basically specify something. uh, so it has now learned that so and so pixel arrangement actually refers to a person. So then using all of this training data or the model, it can then start creating new person images. Okay, so that is where the generation part of it comes. It can create some random random pixel arrangements which look like a person, and that and many more things will ultimately give you something like these networks. Many more things. I'm not even familiar with most of them. Okay, and you must be knowing that like these tools, they don't generate just one output, right? They generate multiple possible outputs of the thing. So if you ask it to do something, it will not generate not just one example of it, it will generate multiple of those. So that corresponds to similar to what we saw here. So there are many possible generations that it can work with. So every input will result in a different output. Okay. And there is something called attention networks, but yeah, that is in fact far more important to all of this, which I'm not much familiar with, so I won't cover that. But there is a recently Three Blue One Brown, the YouTube channel. Yeah, so there is a series of videos about attention. Yeah, maths guy. There's a series of videos from him which talk about the attention networks in detail, and also about the chat GPT and stuff. So maybe you can check that out if you want more details. Okay. Yeah. So I think that is all actually I had in mind for today. If you have any doubts, we will cover those, or we can wrap up the session. So if there are no doubts, I think then we'll wrap up the session. Okay. Yeah. Sure. Thank you for attending also. Are there any doubts? Okay. We'll conclude the session then.